Okay, this is video 1 for my Algebra 3 Prerequisite chapter number 1, in which we are going to be discussing algebraic expressions as well as mathematical models and simplifying expressions. So let's go ahead and start with what an algebraic expression is. Recall that any algebraic expression is going to contain both letters and numbers. Letters, we refer to those as variable values, and they tend to take on many different values, but you'll see several different types of expressions here. Few vocabulary terms we want to get used to, starting with this one here. Any number that is being multiplied by a variable, we refer to this as a coefficient. Okay, so we say the coefficient, say, of x in this expression here is 6, and looking at the expression to the left, x minus 6 here, we say, well, what is the coefficient of this x? Recall that if we do not list it, then the coefficient is just 1, but all of these would be considered algebraic expressions. Okay. When discussing algebraic expressions, you'll notice that some of these contain sometimes exponents. And so let's go ahead and review what we mean by an exponent, or at least what exponential notation is. We say if n is some counting number that is starting at 1 and going up by even increments, we say that we could express something exponentially as b to the n is equal to b times itself n number of times. So this n right here indicates the number of factors in the product with b with itself here. So using this notation, what I want to do is evaluate some of these expressions down here, starting with this one here. Notice that 2 to the 7th, this does not mean 2 to the 7th, this does not mean 14, okay? It does not come out to be 14. It's not multiplication. What we really mean is that we have 7 factors of 2, 7 factors of 2. So if we were to multiply 2 times itself 7 times, we get 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, and times 1 more is 128. So we say 2 to the 7th we would say is 128. Now this next expression here, you'll notice that I have negative 3 squared. One important thing to notice is that these two expressions are actually not the same thing. When I look at this negative 3 squared, we look at this as negative 1 times 3 squared, where order of operations would say we do the 3 squared part first, which means when I take 3 times itself twice, I'm going to get negative 1 times 9, which comes out to be negative 9. So negative 3 squared would come out to be negative 9, whereas if I were to do negative 3 squared and I include the negative in parentheses, this really means, recall, the base times itself that many times. Okay, and you'll notice that I use the word base here. Okay, so the base of the exponent is the part being taken to the power, whereas the exponent is this counting number that we're taking to the power of. Okay. Speaking of order of operations, okay, when we evaluate algebraic expressions, let's go ahead and define what we mean by that. We say evaluating really means to find the value of an expression for given values of variables. So often we'll have a variable expression like this, and I'll say, you know what, go find the value of this if x were to be equal to 9, which means we'll just go plug it in. Because we have so many operations going on sometimes, we have several operations, we're going to have to decide to follow what we call the order of operations. And you've probably heard this. Please excuse my dear Aunt Sally. But basically what we're going to do is we're going to perform the innermost parentheses and work outward as much as possible. And that's what this P stands for, following up with exponents next. Now the important thing I want to point out is this. When you do your multiplications and divisions, you do them as they occur. That is, you do them from left to right. So it's not necessarily true that multiplication in an expression is going to come before division. Okay, maybe division then multiplication, you do it from left to right. So let's go ahead and take a look at this expression that I've given us here. We have 8 plus 6 times the quantity x minus 3 squared, and I want to know what would this be equal to if we were to plug in 13 for the value of x. So the way we do this is we'll simply substitute, is what we call it. And I'm going to put in a blank set of parentheses first and say, well, really what we want to do is we want to plug in this 13 here. So according to the order of operations, what we would do is we'd do the parentheses first. 8 plus 6 times 13 minus 3 would be 10 squared. Now the next step here would obviously be our exponent. So we're going to say, well, 8 plus 6 times 10 squared, we need to do our 10 squared next. So we say 8 plus 6 times, well, 10 times 10 is going to be 100. Following up with this, we say, well, now I notice that I have some multiplication in here, no division, but I'm going to have to do that next. So 8 plus 6 times 100 is 600, and then finally we can carry out our addition. So we get a final value of 608 when we evaluate this. Okay. So last thing I want to talk about in this video is that sometimes we use formulas as a model to model a situation, and a model is just that. It just kind of gives a general idea of what is going on with a given situation. It doesn't give it the exact values that the data actually gives you. So and notice here that it says the bar graph in figure P1 shows the average cost of tuition and fees for public four-year colleges adjusted for inflation. And we say that the formula is this. And this formula here, it models the average cost of tuition and fees, T. So we say that this is the cost, the average costs, putting that average there, for public U.S. colleges for the school ending in, year ending X years after 2000. So one important thing to notice here is we say it's X years after 2000. So at 2000, we could say that this X value is really truly 0. 2001 would really be 1 year after that. So this is X is 1, and so on and so forth. But you notice that what they've given us here is some quadratic model that kind of says, I can tell you the average cost if you were to be able to tell me how many years after 2000 you would be attending college at a 4-year school. So using this formula, what we want to do is find the average cost of tuition. In other words, let's find T and fees at a public U.S. colleges for the school year ending in 2010. So what is our X value that we're plugging in here? Well, 2010 would be 10 years following 2000. So we're going to go ahead and plug this into our model. And what we get is this. We say, okay, well, 4 times 10 squared plus 341 times 10 plus 3194. So to evaluate this, again, what we're going to do is we're going to use our order of operations, which would say inside the parentheses. We have nothing to do there, but we do have an exponent right here. So 4 times 10 squared is going to be 4 times 100. We can go ahead and carry out this 341 times 10 if we want to work ahead a little bit, because I know I'm going to do multiplication next, plus 3194. And then finally we could say, well, this really comes out to be a value of 400 plus 3410 plus 3194. And so all we need really is a calculator. We could type this in very quickly here. We say 400 plus 3410 plus 3194, and we get a value of about 7,000, let's say 7,004, and we're measuring this in dollars. So one thing I want to do is follow up with this. It says, by how much does the formula underestimate or overestimate the actual cost? Well, we can see here that in 2010 the actual cost was $70.20. So it underestimated by, it seems, $16. So that's why we just refer to it as model.